Hi everyone, my name is William Falcon. I'm the creator of PyTorch Lightning, and today I just want to give you an overview of how to convert your PyTorch models to PyTorch Lightning. I wrote Lightning while I was doing my PhD at NYU and Facebook AI research. My academic research interests are in self-supervised learning, and when I got to Facebook AI, the projects that I was working on required a ton of compute. That's when I started working really hard to get Lightning to be super seamless to do things like grid searches across hundreds of GPUs, or even train a single model on a few hundred GPUs. Although we have a lot of demos online with MNIST specifically, I wanted to give you something a little bit more complex so that you understand how to bring slightly more complex projects into Lightning. Lightning can support any complexity project, since PyTorch Lightning is really just organized PyTorch. PyTorch makes it very easy to do deep learning. The problem comes when you're building multiple things or when your project starts to grow in complexity. For instance, your project might start simply where you can train it on CPUs while you're debugging it. But as soon as you try to do anything more, maybe you have to jump on a GPU. At that point, you're going to have to go back and refactor your code, and that's going to be non-trivial, and you might introduce bugs. But you might say, well, adding a single GPU to PyTorch is not super hard. Yeah, I totally agree with that. However, if your project starts to be super slow and maybe an epoch takes 7-10 hours, or maybe if you're training on ImageNet, maybe 3-4 days for one epoch, then you're going to want to start looking at multiple GPU training as well, or TPU training. That's where Lightning can really shine. You can, without changing your code at all, start running on 256 GPUs, 8 GPUs, 4 GPUs, it doesn't really matter, or even TPUs. In addition to TPU and GPU training, Lightning offers out-of-the-box 16-bit precision training. 16-bit precision training can help you leverage certain GPUs like the V100 or 2080 Ti's, where you'll get anywhere from 3 to 8x speed up just for using those GPUs if you're using 16-bit precision. There's a second advantage. If your batch size is too big, 16-bit precision can drop that memory usage by half, which means that you can now double your batch size and cut your training time in half at a minimum. Again, that's without changing your code at all. So this is the Lightning repo, and I want to point to you a few things. One is that our code is rigorously tested. So as you can see here, we test across all versions of PyTorch, so that if you use Lightning, you know that your code will be compatible with 1.1, 2, 3, 4, or 5, unless you're doing something very specific to your code. What this means for you is that there's now a ton of research code that you don't have to figure out if you did correctly or not. So you can focus on actually the research component of your research as opposed to trying to figure out if you did creating clipping or accumulated batches or GPU training correctly. Next, I want to give you a very quick tour of the repo. So if you want documentation, there's a docs button here. And if you want to chat on our Slack, you can click on that. Our documentation is pretty thorough. You can get on here and look at anything you want. I suggest you start with the introduction guide and work your way through here. I'm going to walk you through a fast version of the introduction guide where we're going to refactor a VAE into Lightning. When I start refactoring a project, the first thing I do is I try to find where the core magic happens, right? So the training loop. So in this case, it's likely on the main.py. So we browse this file, and then I see that they have their network definition, pretty standard. They have their data loaders here, that's also pretty standard. And they have a bunch of arguments. Then they instantiate their model here. They get their optimizers here. They have their VAE loss here. And the training loop is here. And so this looks pretty straightforward. You have a test loop here as well. And then you have your if main. So all in all, this is not a super complex project, but this video is intended to be a mid-level project. In the next video, I'll cover refactoring a more complex project that might take longer. So let's go over into my IDE where we can start to develop this. Great, so now we're ready to get started. All I've done now is create a single file called vae.py, and I have set up a conda environment with PyTorch Lightning and PyTorch. So as a sanity check, I'm just going to import torch and print some tensors just to make sure everything's working fine. And great, so now we know we're all working. So the next thing that I would do when refactoring a project is decide how many loops do you want? Do you want a training loop, and a validation loop, and a test loop, or do you just need a training loop, and so on? So Lightning makes all of those optional. In this case, let's just start with a training loop. So the first thing I'll do is I'll go into the VAE file and find where the network is. So here is the VAE project, and here is the main VAE. To get started, I'm going to just copy this guy into the Lightning project. So I delete this, and I have a few errors. I'm going to do the imports. Great. So again, this is just pure PyTorch. So I'm going to go ahead and just import Lightning now. And I'm going to replace this module with a Lightning module. Okay, still the same. Great. So again, a Lightning module is just a torch module, so this here should still work. Okay, so it looks like we have a bug, and in this case, I'm likely just importing the functional incorrectly, so let's see where that's coming from. Okay, great. So now we change this, and this should be fine. Okay, so our model trained without problems, and let's just print that out just so we're very clear. So again, nothing's changed. This is just a torch module still, no problems. So Lightning, all it does is it gives more methods to a module. So to get started, make sure that we set up a trainer under debugging conditions so that this can be a lot faster. So I can figure out if I have any bugs or not. So the first thing is I can just init my trainer here, trainer, and I'm going to set fast dev run, which will mean that it's going to run a single batch through a training loop, a single batch through the validation loop, and tell me if there are any errors. So this is basically like trying to compile your code. So this is kind of one of the first nice things about Lightning, is that it's very focused on research so that you can move through this a lot faster. But once you're done, you can take this into production without any problems. Okay, so now when I do this, I'm going to get a ton of errors, and specifically because I haven't added a training loop nor a validation loop to my model. So let's just debug to verify that. Lightning should give me errors about this. Okay, great. So Lightning told me that I need a training step. So now I'm going to add a training step. So in the training step, I'm giving the batch and the batch index. So to figure out how exactly to structure this, I'm going to just look at the documentation. So I go here, and then I go to my Lightning module. And then here I have a minimal example. So I can look through this and say, okay, this is exactly what I need for the training step. So for the training step, I'm going to get my batch of data, then do whatever operations I have, and then I'm going to return this dictionary that has my loss in it. So now to figure out what happens in that training step, I'm going to just look at the original code, and here's everything that happens in the training step. So you have your batch of data, you do the zero grad, you run your model through, you run your data through the model, you have a loss function, and then you have this loss here, and then you apply loss.backward. Okay, great. So let's just copy all of this stuff and put it into our Lightning module. So training step comes here, and I have exactly this. Again, since in Lightning you don't deal with GPUs or TPUs directly, I'm going to delete all calls to devices or anything to do with CUDA. So I delete that. Also, we update the optimizers for you, so you don't have to worry about when that happens. So I'm going to delete these guys. And we also aggregate the loss exactly how it's done here across each training step. And that's pretty standard across every project that you're going to do. So now, since I am inside the model itself, I'm just going to call self instead and pass in my batch, which is this guy here. Now, my loss function is, let's see here. Okay, so now we need to figure out what this loss function is. So let's find it. My loss function is defined here. Great, so this is my loss for, looks like my whole elbow. So you have the the reconstruction loss here, and then you have the KL divergence. So I now am going to add it to my model. So I'm just going to say, here's my loss function, but I am inside the model, so I need to pass self. Great, no problem. And now I call that directly. And then again, this is called batch, not data. So I get my loss. Now Lightning automates the backward as well for you, so you don't have to deal with that. So I'm going to delete that. And then instead I'm just going to return a simple dictionary with the keyword loss, which lets Lightning know that this is the loss that it needs to optimize. Okay, so that's just my training step. This should now work without any other changes. Okay, great. So Lightning says, well, you don't have a data loader. Okay, so there are a few things you can do. So with Lightning, you can, so we're going to find the data loader first. So in this case, we're using mthis. So this looks like the training data loader. And I can do one thing very simple. I can just bring in my data loader here. And I guess I need to import all of these dataset things. So here we go. So I import these guys. And then I need args. So I'm just going to do a very quick Argparse. Looks like they have batch size on here. Great. And that is all I need. Now these k args, we just want to make sure that nothing else is being passed in. So okay, so it looks like they're also passing these guys in. So we're going to define those. And here they are. Okay, great. So now with this, when I call fit, I can also pass in my train data loader. And since this is a CPU machine, we're not going to run it. Great. Okay, so it looks like everything's working. And we didn't add an optimizer. So now Lightning tells us, hey, you need to add an optimizer. Okay, great. So now we go back and find where the optimizer is. And we say, okay, here we go. So the way you add the optimizer in Lightning is you just, as the message tells you, so we try to be very friendly with messages. So you need to add a configure optimizers method. Great. And we are inside the model, so we're going to pass in self parameters, and this is inside torch optim. Great. Okay, so now we have an optimizer, and this should work now. So I run again. Okay, so it looks like I have an exception, something about view. Okay, so it looks like forward is getting now a list, and it doesn't, and the list can't be viewed. So something that's super nice that you can't really do in things like TensorFlow is debug code like this on the fly. So I can see exactly what is in here. So now I see that it's tuple, and then I want to know what the shapes are here. So that looks like an mthis image, and then this looks like all the labels. Okay, great. So now we want to say, well, okay, so here's a problem. We forgot to split our batch into an X and a Y. Again, this is what happens inside the training loop, and inside the training loop, you normally split your batch into X and a Y. So now I'm going to change this, and then I'm going to also change this here. So my loss function expects my reconstruction X and my X as well. So I just want to make sure that we have that, and that is in fact true. Okay, great. So we don't need the Y, so we're going to do that, and then we run again. Okay, great. So my training completed. It did one batch, one epoch, and it calculated a loss. So now if I turn this off, I should be able to have my model training. Great, and you can see it down here that the loss is in fact decreasing. I don't have a validation loop yet, so this is just training loss, but everything looks like it's working correctly. So now let's go ahead and add a validation loop. Okay, so now we're back at this main repo, and now we're adding a validation loop. So we're going to copy this data loader and bring it here into the Lightning. So there is my validation loader, and I'm going to just pass it in now into my trainer. Okay, so Lightning tells me that I passed in a val data loader, but I didn't pass in a validation step. So again, we need to know what happens inside that validation loop. So we're going to just copy paste exactly what's in the training step. In this case, I don't want to do anything differently. So we'll do validation step. So this should be fine. Let's double check to see what the actual original repo does. So here we have, again, we're just passing data. We have the model. And then this looks like some comparison stuff. What is this? Right, so they're showing some reconstructions. Okay, so they want to log some images. Okay, perfect. So why don't we just do that as well? So let's go ahead and copy all of this from the validation step. So we do want to leave the batch stuff there. Okay, so again, we don't need the CPU nor the tocalls. We are inside the model, so we're going to change that. And we're going to pass in X instead. And then we don't need this, so we know what our test loss is. In this case, validation. And it's a function within our class right now. And then again, this is just X. Okay, so now that we have our val loss, it looks like they want to log an image every now and then. So in this case, we want to check that the index is 0. So the first, looks like just the first image. And we're going to just replace data with X, data with X, and now we have the save image function. So we find out what that is. Okay, so we have save image, and we're going to just paste it here. And import this image from pill. Great. Okay, so now that this works, we're going to just do that. So for epoch, LightningModule actually tracks this. So it's self.current epoch, and it's the same thing. And then since we're in validation step, and this is the validation loss, we're going to just return the validation loss. So I'm just going to run this because I want to be faithful to the original repo, and this is going to give me a validation loop now as well. Okay, so it detected that we're trying to shuffle our validation data loader. So that is actually a bad practice. So we just caught a bug that should not even happen. That's actually on the PyTorch repo. So again, Lightning really makes it easy so that you don't mess up things that you should not be messing up. Okay, so now n row, we don't really know what that is. Let's look at what they had. Save image. Okay. So it looks like it's part of save image. Huh, that's weird. Okay, so I'm not sure we need that. I'm just going to go ahead and delete that. And this should be fine now. So what is all of this? This is the path, it looks like. So let's just refactor this a bit. And we just pass in path. Okay, now let's see if this works. Okay, so it looks like this data, so we passed in data again, and we're trying to clone it somewhere. So where was this? Okay, so data again is not a tensor, so it means that we're not passing the correct thing. So we look at image again, and the comparison here is cat. So we want to know what comparison is. Let's see here. So again, this is something that you can't really do on TensorFlow, but here I can actually inspect the things that are happening. So this is not a Lightning thing, it's just a PyTorch thing. So I can see that it is in fact a tensor, and just double check that our path is correct. That's fine. And then we step inside this guy. So we have a file name. Okay, so that's a problem. We swapped the file name with the data. Okay, so more bugginess. We'll just do this. Okay. Alright, we have another issue. So save image. Axes don't match array. Okay, what does that mean? So probably means that the shape of this guy or this guy is not 3. I'm going to just guess that real quick, but I'm going to debug this first to make sure. So again, this is one of the beautiful things of PyTorch. Okay, so I can look at my image. Let's look at the shape of this. Okay, 16 by 1 by 28 by 28. Okay, so that's interesting. So let me just experiment real quick with a test, and we're going to just do this. Okay, great. So that is a problem there. So it looks like I'm just going to take the first image and not the full batch. Okay, great. So that fixes the problem. And then we just want to make sure that the rest works. So we're going to do this. Okay, that's interesting. Cannot handle this data type. Okay, looks like we forgot to add mode on this from array, so we're going to do that. Okay, so apparently we also did not make this file. So let's go ahead and change the file name. Great. So now we have this, and we have everything working correctly. So now my epoch is running, and unfortunately this validation step won't be called for a while. So this is again another trick that Lightning can do. So I can skip straight to it by setting up my fast dev run just to make sure that this worked. So I can do that. And then what we'll see is that we're going to run through our whole training and validations loop once. Great. And then that should have printed an image. And I can see my reconstruction. It's not great, but it's there. And now let's just say I want to train on 10% of my data just to see what the reconstruction looks like without waiting too long. So I can change this and say, okay, I want to use only 10% of my training data. And my first epoch is going to be a lot faster. So you're starting to see some of the benefits of refactoring into Lightning, is that you don't have to add any of these features yourself, which makes your research flow a lot faster and lets you focus on exactly what you want to be focusing. Okay, so now we're going to change this a bit. In the case where you're doing faster iteration on things that might change your data sets, then you want to use this format where you pass in the train and the val data loaders into your fit. However, Lightning lets you do a better definition for research, which is inside the actual module itself. And this means that you don't have to figure out where the data came from, how it was processed, etc. So let's go ahead and do that. So all you need to specify are your training data loaders and your validation data loaders. Okay, so what we're going to do is now copy this into there, and we're going to return that. And this args will still be available because there's a main file, but we're going to generalize it in a second. And we're going to pass our validation there as well. And now we have our val loader. So again, just to make sure that everything's working, we're going to remove these calls here. And then we're going to do our fancy compiler trick and just say fast dev run equals true. Great. Args isn't available here, so I'm going to just remove it. We don't really need it at the moment from these data loaders. And great. So now I just verify that everything works again. Okay, so everything worked. So why is this better? That's because when someone looks at your code on GitHub, they're going to be able to know exactly only the things that went into this research, right? So you'll be able to see what the model was. You'll be able to see exactly what the loss was. You'll be able to see what happened in the training step. So this is where a lot of things get super complicated, and when you get into GANs and different things, this gets really crazy, and people don't know necessarily where the magic specifically is happening. And then you have your validation loop. So what happens there? And then your optimizer, and then your data loaders. So let's just make a slight modification here. So we want to make this even more clear about what's happening in the training step. So since this is a VAE, what we are going to be using this mostly is for reconstruction. So we're going to give it noise, and then it's going to give us back a reconstructed image. So we're just going to modify this forward because this is actually what's happening in the training step, and we're going to pass it here. And then we're going to, so in the training step, we have our encoder, then we draw some noise, and then we pass it into our decoder. So we do decoding here, which is the only thing that we really want to do from our model when we do use it in production. So here we're going to say self.decode, and we're going to pass in z now. And now all we need to do here is say x hat equals self.z. And that is the only thing that we need to change. Great. And then our reconstruction is going to be x hat. Cool. So now we modified this. So now when I call this VAE later, I can just use the decoder and give it some noise. So I run this to verify that my changes worked and there are no bugs. Okay, it looks like I have some sort of bug somewhere. So I have something mismatched. So let's just double check this again. So I take my x, I run it through the encoder, I reparameterize, I have my z, I decode my z, that gives me an x hat. Where's my decode? Okay, that's fine. And then I'm going to pass into my last function x hat, x, mu, and log var. And my last function has my reconstruction x. Okay. So where exactly is the bug? It's coming from our validation step. So we need to go ahead and change that. Right, so this is validation step. So it's the same thing. So we're just going to copy this guy and move it into a validation step. Okay, and reconstruction batch is now just this. And my val loss is this here. Okay, so now we rerun this to just make sure it works again, and fast dev run will let us know if there are any bugs. Okay, no bugs, great. Finally, the last thing I want to do is, I don't really want to use this this logging situation that PyTorch has here. So I'm going to just use tensorboard to do that. There's a hook to your module, where there are many hooks, but here's one of them. It's called validation epoch end. And in this case, I also want to have my validation loss not just per batch, but I want it for the whole epoch. So this is a good place to add this as well. So this outputs is a list of dictionaries for whatever I passed in on my validation step. So validation step, I passed this in, so that means that I can iterate through this, and pull out exactly that key that I passed in. So that was a scalar. Okay, so now I can just take the average and send that back. So again, this is just for logging or whatever I want. So in this case, because I want to log this to tensorboard, and then I have to pass in this keyword called log, and then pass in the dictionary of things that I want to log. And that will automatically get pushed into tensorboard now. Now we allow other loggers, it's not just tensorboard, so you can configure one or multiple of those. Okay, so now we added validation epoch end. So I made some changes, I just want to make sure I don't break anything. Okay, so everything works. Now I'm going to remove this logging stuff, and I'm just going to use tensorboard to do that as well. So self.logger.experiment, and then I just do whatever I can do with tensorboard. So I actually want to save this image, the reconstructed image. So I'm just going to pass it in also to my output. So pass that, and now I have it here. And I can just say, well, give me, I just want to log one of them. So I'm just going to pick outputs, and I'll pick the last one. Now I can delete all of this. Great. And now I can just do whatever tensorboard does. Okay, so self.logger.experiment is just my summary writer from tensorboard. So here I have some utils to make images out of this stuff. So I'm going to just pass this here. That's going to give me a grid. And then my writer is just self.logger.experiment. And I'm going to add that image there. And then I also need to import Torch Vision for this to work. So I'm going to just say import Torch Vision. Okay. So now that should log images. So again, I want to make sure that this works. So if you didn't have Lightning, you would have to somehow figure out how to skip the training epoch and go to the end of your validation to see if this code has any bugs. But instead, because I have fastdev run on, I can just test all my code immediately. So if this adding image doesn't work correctly, I'll know right now. Okay, but it looks like it did work. Great. So Lightning has automatic tensorboard built in, and you can see I've been debugging things, but I have all of these experiments, and every single one of them has been versioned. So I don't have to do anything or log anything. So now I can just start tensorboard and look at exactly the outputs of that. And now I see all of the experiments that I've been running, but I just want to look at the last one because that one has the images. And I see that I have something that isn't great, but the image was logged, so that's great. So I don't have to do anything here. So if I want to log on tensorboard on trainer, I go to my training step, and then I add just logs again. So this keyword called log. So I usually do this to make this simpler, because I can name it something different now. So I can say train loss, and then pass in my loss. And now I'm going to say log is my training loss as well. Great. Okay, perfect. So now I'll be able to see a loss happening on my training once this experiment gets saved. Okay, 37, here we go. And we will see our training loss here. Okay, so now you can see it happening. Okay, I'm going to show you a few other things. So one, a validation epoch end, I'm going to add another key called val loss. And this is going to trigger model checkpointing automatically. So I pass that in, and as soon as I do that, and I'll set this up to only train on 10% of my training data and 10% of validation data, just so you can see what happens to Lightning logs. And when I run this, it's going to start automatically saving checkpoints for me when there's a new minimum val loss. You can obviously configure all of that, but it's built into Lightning if you just want to do it very quickly. There's a callback called auto checkpoint where you can specify on what keys and when you want to save stuff. Okay, great. So now we have my epoch here, and we can see that Lightning saved a checkpoint after epoch 0. Okay, the next thing I want to show you is what are some of the other features that you can get by just converting your model into Lightning. So the first thing I want to do is I'm just going to parameterize this So trainer has a lot of arguments, and I don't necessarily want to be adding them one by one, so I'm just going to add them to Argparse like this. So now I have all of the trainer arguments available. And so that the trainer can instantiate with those arguments, I'm just going to pass this in, and I'm going to say from Argparse args, and I'm going to pass in my args. So now this lets me do really cool stuff like pass in the number of GPUs and the number of nodes automatically. So I just want to make sure that this worked. Okay, no problems there. And obviously you can continue to add things that Lightning would expect, such as this, and you don't have to specifically pass them in through the Argparse. So, okay, so that ran fast dev run. Okay, now I'm going to take this into an environment with 4 GPUs, and without changing any of this code, I'm going to show you exactly how we can do multi-GPU training. Okay, so I'm in this environment, and now I see that my project is there. So now I want to show you that we have a few GPUs available here. So we have 4 2080 Ti's. Again, this is just the same VAE, and nothing's changed. There's no CUDA or anything like that, so just to show you that. Nothing, and also .2. Okay, well, no actual .2. Okay, perfect. So it's the same code. So now I'm going to create an environment. I'm going to activate my environment, and I'm going to install PyTorch. PyTorch is installed. Now I'm going to install PyTorch Lightning. Okay, now I just want to show that the VAE, again, is still the same. There are no CUDA calls, nothing. And now I'm going to just do a very quick test to make sure this works. Okay, so looks like that did work. Now I'm going to run this on multiple GPUs. But first, I'm going to create a new screen so we can monitor the GPU side by side. Okay, so this is going to be our screen where I run the code, and this is going to be the screen where we monitor. So we're going to say NVIDIA-SMI, and I see all 4 GPUs here. So now I go back to my code, and then I say Python VAE, and then I'm going to say GPUs, just 1. So in this case, I want to just train on the single GPU. And you can see Lightning detects the GPUs, and it picks 0 as the index of the GPU, and it starts training your model. So now it's much faster. And again, you didn't have to change anything about your code. So now I'm using 10% of the GPU and only 807 megabytes. Okay, so we have a bug with the batch size thing. So this should be an integer. Let's see here. Batch size default type equals, and that should fix it. Okay, now much faster. Now we're going to use multiple GPUs. So if I just wanted to do 2 of these, I can go ahead and do that. And Lightning uses DP by default, but I actually want to use DDP, which is distributed data parallel. That's the recommended way of doing multi-GPU training instead of using DP. In DDP, every single GPU runs its own version of the model and only syncs gradients. Okay, now I'm training my model on multiple GPUs, and you can see that I'm using both of them here. And notice I don't have to do distributed sampler or anything like that. Lightning automatically adds that to your code. You can turn that feature off if you don't want it. But in this case, I split my data set into 2, and I'm training half of it on one GPU and half of it on the other, and then syncing gradients across. Okay, so now I want to use 4 GPUs. That's very easy to do. So I just change this flag here, and I'm using all 4 GPUs. Okay, now you can see each GPU is doing its own thing, and I'm using effectively all 4 GPUs. Now I want to show you another feature, which is precision. So in this case, if you want to use 16-bit precision, you can do this. However, we need to install Apex for anything that's PyTorch 1.5 or earlier. The Apex install is non-trivial, so instead I'm just going to install the latest PyTorch, which has built-in Apex support. Okay, so it looks like we now have PyTorch 1.6, so now we can just run 16-bit precision very easily. Okay, so it looks like we need to modify our model just a little bit to be able to use 16-bit. So because PyTorch autocasts a lot of things under the hood when using this mode, we're going to change our cross entropy to use cross entropy with logits. And now we should be able to work normally. Okay, great. So now we're training. So we're using 16-bit precision on a single GPU. Great, so in this video I showed you how to convert a PyTorch model into PyTorch Lightning, and I showed you that although the model is super simple, we were able to get really advanced features by just converting to PyTorch Lightning, things that you would have to code on your own and probably test, and it would take a while to get correct. But this way you can iterate through projects and move across GPUs, TPUs, and any kind of device that you want without any changes to your code whatsoever.